So I was working on 40 years back. So you're for a while.
Okay. Let's get going. So how is it? How is the homework? Reasonably good. Progress there. Try to work a little harder. But anyway, yeah. So yeah, thank you for fixing my Japan's mix error. Like we never tested on x86, so it was working on ARM for us. What I was saying. Okay, cool. So I'll do my office hours tomorrow. Just quickly, what time will work? Something like 4 p.m. works, or what is an ideal time for you guys? 4 is okay. Okay, let's do 4, and let's like tentatively like put it as my office hours. Since we have a homework, you can come talk to me. So in the office, but I can also provide Zoom if you want to Zoom, like this Zoom, for example, as well. But probably in person is better. So what else? I mean, today, like tomorrow, I can do in person. Maybe there will be days when I will travel. So okay, cool. So today we will try to talk about exceptions to make sure that it's our kind of like logical next step. So we, assuming that you're done with your homework, we can boot into 64-bit Rust, right? And some people say we're not going to use grub, we will just boot on our own bootloader. That's fine. But that's actually quite challenging and exciting. Do whatever, but let's at least like boot into this 64-bit version of Rust, and then today and maybe Monday we'll talk about exceptions. The next homework will be about exceptions. The reason for that, I mentioned it earlier, is that if you understand how exceptions work, then you know when your kernel crashes, at least you get your exception handler, and at least you can read the error and understand, okay, maybe it's a page fault, maybe it's a segmentation error, maybe something else. It's easier to debug, right? So it makes sense to set up exceptions, and then we will start talking about how to build a memory allocator. And after that, we have the memory allocator running, and then after that, we say, look, enable user level. And after that, we will try to load something into user level, like another binary. Right? So that's the plan. Okay, exceptions. So does anyone remember how they work from x86 class? Who can give me an overview? A quick overview. We all kind of talked about it. I like how everyone quickly looks down.
I'll ask you questions. So exceptions are a form.
Wow, there's a ton of names. Like back in the days, people were specific about names, and today I prefer just two names, the two words: interrupt and exception. An interrupt I will use for an asynchronous event, meaning it comes, you're running something and it just comes from a device, and the CPU is interrupted, and you start.
Like interrupt.
Yeah, for a keyboard, like for a timer or something, right? And exception is that when you hit a condition, you have to like react.
So what is this called?
It used to be, I mean, yes and no. So you can, in x86, we implemented exceptions or implemented system calls using an in some number instruction. In a way, in my terminology, I would say it's an exception, but it's not like a catastrophic condition, right? So again, you can catch me on this. I don't really know what's the right way to call it, but it's synchronous, right? Because you're invoking, but something like division by 0 is an exception. You touch a page is not mapped, it's a page fault exception, right? Just because, you know, there is no way to move forward until you kind of like say, okay, I know what to do next. So that's an exception. So like I simplified it a lot, but I think trap, and I'm not 100% sure that I remember it correctly, there is a flavor of an interrupt or exception which either disables or does not disable further interrupts. So you can configure it in an interrupt descriptor table, right? And I think trop is one of those, but let's not like, it will be clear from the context. I don't want you to learn all these words. It doesn't really matter that much, to be honest. And on other CPU architectures, it might be different. But anyway, so then if we kind of like shy about it, I'll go through this.
I can try that when I answer you.
Sure.
I might be mixing up interrupts and exceptions a little bit, but essentially you have handlers for all the different exceptions that occur. When the exception is triggered, you save state and you invoke the handler. You may or may not need to do a definition of a switch depending on that. You save state and the exception.
Correct. At a high level, yes. So there is a hardware table, and I prepared to teach it, but I am glad that you remember and can actually explain it. There is a table called interrupt descriptor table. It's just you put it anywhere in memory, and then you just put the pointer to this table in a special hardware register. This is how the hardware finds this table. The table contains, I think on Intel, it's 256 entries, and some entries, the lower, I think 32 are reserved by Intel, and I think they grow this reservation, so maybe it's 48 now, but I don't remember. But and the lower, let's say 16 are well defined, or the lower 32 are well defined. There will be like division by 0, H fold, whatnot, and the other are configurable, and you can configure a device, a hardware device, to send you an interrupt through one of those vectors. And there will be a specific protocol how you explain the device. Okay, please send me like exception or interrupt on a number 55, for example, or something, right? And they're like, well, again, canonically used the first 16 like will be called IRQs. And what does it stand for? I already forgot. Yeah, IRQ. Something, right? And but maybe Google and tell me. But anyway, so those like for the timer, but a lot of these you can reconfigure actually, and like real networking. If you have like a modern network interface card, first of all, it might support multiple vectors and send you like you can route the exceptions to specific cores and involve different vectors, but you can like talk the specific protocol with device to negotiate which interrupt you will be using. Yeah.
So the vectors that are assigned to devices, they will differ from because
it's up to you. Like, and we as designers, we can choose which vectors to use. Only like the lowest 32 are fixed. But
for example, like vector 55, I have a network already. I get a new accelerator from the which is also configured to use vector.
I don't think. Yeah, that's a good question, and I actually don't know the details. I would assume these days, modern days, old days, you really physically had to like put something like a piece of, I think it was called a jumper, like a tiny connector on the card to say, look, please deliver on number 16 or something. Today, everything is in software, so you can negotiate and it will deliver on a specific number which you configure. Plus, I should also read up on this. I think you can also talk to the interrupt controller, and that will route it in a specific manner as well. But also what I wanted to say, if I remember correctly, you actually can share an interrupt, and then it's up to you to distinguish which device triggered it. This is rare because it's like typically you have enough, so you may run out, especially you may run out if you say, look, I have a machine, it has 128 cores, and I want my network adapter to essentially route, like specifically, there's a technology which allows you to say, it's called receive flow steering. So say, when I receive a specific packet which matches a specific tuple, say from a specific address or it's a specific flow, route it to a specific core. This allows you to process the same flow on the same core to kind of achieve cache locality and stuff like that. So at this point, you say, look, a device supports 128 or something. but you only have 256 entries in a table, and maybe you have a couple of those devices, you may run out, and then you might play tricks like either sharing interrupts, or you might have interrupt descriptor tables, which are, I think it might be, that's a good question. I should stop here because I don't remember. I thought that you can also explain to the hardware to route to a specific core, but that I should double check as well. Like. No, like IDT is just one table. There is no interaction. The trick which I was trying to recall, which I was thinking about a while ago, but I don't remember anymore. So I don't want to talk about it. So like, let's come back to it. You can have different IDPs and different cores. And then the question is like, do you really need this trick, or you can route through the same IDT and just at the level of the handler in memory say, look, which core I'm running on, and if it's 0, just use one data structure, and if it's 1, use another. So let's come to this. So that's a good topic of research, and I never really worked in this area, so really never was engaged in like this low level interrupt handling, or like optimizing those non-uniform machines where you have multiple devices and you want to route things locally. But I promise I'll read on it and then I'll come back. So it's too advanced for today. Let's just understand how it works. But okay, so let me just quickly give you an overview, because again, our goal is to set these things up. So quick reminder. So a couple of things which Soham said which are kind of important, is that there might be like, do you guys still remember privilege levels? So what are those? You tell me. Say 0, 1, 2, 3. Which one is most privileged? On input. Into, yeah, most privileged. So we run kernel here. We can configure something to run in these two, but we will use user here. And there are two different cases, whether the interrupt, and in the interrupt table, when you configure it, you can actually configure a switch, meaning that if you're running at user 3, obviously your interrupt handler will be in the kernel, because it's a privileged piece of software. It can like override the entire kernel, reload page tables, do whatever, right? So the way it works is that when the interrupt is delivered, it will fetch a code segment from the table, and this code segment can, like, essentially it can stay at 3, but typically it will switch to 0, right? And this is specifically will switch you from level 3 to level 0, right? Does it make sense? And I will cover it in a second, but that's kind of like the main idea, that even if you're running inside at level 3, like we will later in this class, when the interrupt will be delivered, most naturally through the interrupt table, it will trigger a privilege switch. So we'll switch from 3 to 0, right? And the handler will be running at level 0, right? So we will be able to access the entire kernel state.
Can't you define your own? Wouldn't it be problematic to have?
Say again?
Can't you define your own handlers in the interrupt descriptor table? Like as a user?
As a user.
I thought you could, like, I thought you could like define.
You can, I believe, because I mean, it's a little exotic and we can talk about it. Again, it depends on the use case, right? But in theory, right, you can, this code segment can say, look, by the way, I'll stay at 3.
Oh,
the user handler. So this is possible. If you ask me again, I never seen it in practice. But why would you do this? Maybe it makes sense for very fast user level interrupt delivery, meaning that you say, look, I want to stay at user level. I will never, like, this is the device, I will always use it. It's my, like, this is some application, like, I don't know, web server or maybe it's your whatever. The memcached, which is your like distributed hash table. And like it has access to a network interface and it wants to route interrupts. You want to route interrupts directly to this, to the level 3. That's in theory, it's possible.
Yeah, like, for example, like if you want to make a handle for people, you want to program this.
You can, so like, you can, but then, okay, the problem is the following. Sorry, I actually looked at it, that's how, let me come back. Okay, I'll answer in a second. So the problem with this, does anyone see a problem with this? Let's think for a second. Because I wasn't able to see the problem right away. Go ahead, Sahar.
I'm just like, the only problem I can think of is potentially untrusted code running as part of the handler. But if we already talked about user level device driver, and we also just discussed about how device driver is usually defined. So then putting those two together, it seems easy to imagine.
Yeah, no, like let's assume we want it and we say, look, this user level, once we say, look, we're fine. We don't care about isolation anymore. I mean, we do, but we are very, very careful. And imagine we want to make sure that user program can access a network interface, and the moment interrupt is delivered, like, the moment like certain condition happens, maybe like it's some number of packets are received, the device sends an interrupt to the CPU over like PCI bus. An interrupt goes through the interrupt descriptor table, and it happens to be configured that it's at level 3, so why not? And then it lands and starts executing code of the handler at user level. There are use cases, like really sometimes you want to have exclusive access to the network interface, you want to cut the latency as much as you can, and you say, look, everything will happen at user level. There is a subtle problem here, which Intel tried to solve actually later on in their life, but let's think about it for a second. It's kind of like advanced operating systems question with the star. It's not immediately over.
The problem that you're just like sacrificing.
In a way, but in a controlled manner, because you say, look, this is the network interrupt that routes to, like, let's say entry number 55 as we discussed, but the timer still goes into entry whatever typical timer or queue. I think it's 32, and timer sets TF with this to 0. So once in a while, the kernel receives the timer interrupt and will do a context switch or gain control. And the kernel can take a look at the user code and says, look, you ran for a while on this device driver. Like, I will patch this handler and we'll do, like, I'll take it away from you, right? So it seems that we can retain control, even if we give user temporary access to this device, right?
But could the problem be that, like, an attacker could potentially replace the interrupt handler in memory, or
That's a good question. So can it or not? Is there a way to protect the interrupt table from the attacker?
if the interrupt table is user space,
No, hold up. Interrupt table is kernel space, so it will sit here in this memory of the kernel, right? The hardware can access all the memory. So the hardware register, which points interrupt descriptor table register, I think it's a virtual address actually. So it points to the interrupt descriptor table, which sits in the kernel memory. So the user cannot just directly write into the interrupt descriptor table. It just receives the interrupt. Yeah, and the handler, we're not going to allow user to override the handler pointer, like whatever this one. Let's imagine. Right, we will just have a syscall which allows the user to say, look, my handler will be here. That's okay, we can do it, right?
Okay, so I think I got confused. I think the reason interrupt descriptor tables usually don't allow users to define their own. It's because, for example, if you wanted to do something special when you receive a keyboard interrupt, I think it goes to the interrupt descriptor table, goes to that handler, and then it sends a signal to your process. And then you have a custom signal handler, right? Is that typically how it's done?
Yeah, yeah.
So you don't define an interrupt handler, like a signal handler. It's usually a lot of interrupts end up having signals sent back, I think.
Correct. But imagine you coming to, we're working on a project which says, look, we will make X amount of money if we shorten this interrupt delivery cost by half. And we start thinking, can we? And at this point, we say, look, what are the, and it's a real research question. So I haven't seen a very good design yet in my life, but I'm pretty sure if you start thinking in this class, you can come up with a good one. And you say, look, because if you first go to the kernel and the kernel does an upcall like a signal, it can still be optimized heavily. So the question is how much we're going to be saving, and we can talk about it later. But imagine we want, again, the stakes are so high that we say, look, let's do it. Let's try. If we see an isolation problem, then we will try to find a workaround. Maybe there will be no.
So you're saying some researchers are saying having an interrupt go to an interrupt handler just to send a signal back, that's like a level in direction that can be skipped. Just a direct interrupt.
Correct. Yeah, correct. And I mean, maybe we're doing some high frequency trading or something, just for the sake. I don't know what these people do. Just imagine. Or we're just doing it for fun because we know that we can explore. So in theory, we can say, look, leave it pointed to the user level, right?
What is the interrupt that we define, that user define? That crashes, but that is bugging. That can start having problems.
Well, but if it crosses with a SAC fault handler will lead us back to the kernel, and we will kill the process or send a signal to give it a chance to recover if we want it to give a chance. Depends, right? So that seems to be okay. Although this is all good discussion, so this is all has to be carefully considered. But what is one obvious problem? That's a good observation. So you're saying, okay, by the way, guys, I forgot exactly. It's a CLI or clear the interrupt flag. And is it a privileged instruction or not? And I assume it's privileged on Intel. But maybe there is a way to say, look, you're allowed to invoke it. I'm not exactly sure, but because and it's kind of like a double-edged sword. So you say, look, if I allow user to invoke this clear interrupts, which means that no further interrupt delivery will be allowed, then we're kind of losing our timer, and at this point losing control over the system, right? If we don't allow user to invoke clear interrupts, then the user has to be more carefully written to deal with all possible edge cases where one interrupt goes on top of another. But we can also configure a certain flag here, which disables further interrupts. I forgot exactly what this flag is. But essentially, you can say, look, after the first interrupt is delivered, other interrupts are disabled. And it's a double-edged sword, because if you say, look, user runs here forever and never tells us to re-enable interrupts, then we kind of stuck losing control, right? So we have to make sure that, maybe it's not a good idea. We'll leave interrupts always on, but then user might be overloaded. So that's tricky business. I agree with that. Worth considering, and I don't know a good answer, but it's kind of this is all the problems. This CLI is actually not something I was immediately thinking about, although you're right, absolutely. But the subtle problem, which I was which I was concerned about, is that remember, this interrupt handler lives inside the address space of process 1, for example. What if we did a context switch and we switch to process 2? Well, maybe we want to support, you know, context switching and multi-processing, right? Then the question is like, what happens now when the interrupt is delivered and the interrupt handler goes into this like vacation, but we are now in process 2? What do we want to happen? Because the interrupt handler was inside process 1, now we are in process 2. And again, like there are certain solutions which you can think of. You can say, okay, well, I will multiple solutions. One solution, well, change the interrupt descriptor table when you switch from P1 to P2. Just say, well, look, this one goes back into the kernel. Parallel to like fast interrupt delivery, but that's kind of okay because you're not even running P1. So what kind of fast thing you're talking about? You say, look, right now I will be delivering into the kernel, and your handler in the kernel can say, look, I will switch back to P1 and continue inside P1, which is a meaningful kind of strategy, right? Another idea is maybe you can leave some kind of a stub handler inside P2, and the interrupt, you should probably somehow make sure that the execution environment of this handler is protected, meaning that it at least has stack or something, which is kind of hard because you don't trust P2. P2 might, but you know, you can maybe configure the stack switch on the interrupt delivery, and then this stop handler will go into the kernel and say something like switch to P1, because you say, look, clearly this P1 is the one which needs this interrupt the soonest, right? So, but you see that like the space quickly starts exploding. That's why I never seen it in my life, like anyone finishing it. Although in theory, all these corner cases can be somehow sorted out, but you have to be very, very careful to make sure that, you know, you handle interrupt disabling, you handle whatever happens on the context switch. So, but in theory possible, if you have a very appealing use case and you say, look, I wanna shorten this pass question.
I was just thinking if this context switch problem could be solved by creating the interrupt handler with a shared library. Those shared libraries will need to be.
Yeah, you mean like you're saying that at a specific address in all the processes we will have the handler. Right, you're right. But maybe we want different behavior, because really if we want to optimize for P1 and P2 is some goofy program, your logic is kind of still switch back to P1, right? No matter, that's why I'm saying the handler might be slightly different. Right?
Like you to process the thing you still need to.
But the real problem here is how to make sure that this execution environment for inside P2 is secure, meaning that P2 itself cannot write into this stage. P2, what else can go wrong? Like we need a stack in most cases, although you can write a sequence of code which it executes without a stack as well. So that's also doable.
So I'm just to make sure, for signal handlers, each process, like there's the kernel has a data structure where it can check to see a process's specific set of signal handlers, which are usually default for most of them. So maybe we can do something similar to that if we wanted user level, you know, descriptor tables. Maybe you have this data structure where you check with the vector, and if it's null, you just use the normal one. Or if it isn't null, then use that.
You lost me a little, but what kind of what?
So when you get interrupted, there's a vector, it's like the index into the descriptor table.
Yeah.
So maybe before you check the table, you check this other data structure to see if there's a custom.
Yeah, but
that is kind of that.
No, but it also requires custom silicon, right? Because the logic of going through the interrupt descriptor table is implemented by the CPU.
Oh, I see.
So at least on Intel, so you cannot override it. You can, like the moment you get your handler, then it's software, right? Everything else before that is hardware, which is also a good clarification. So, but I think it's possible. So related area to this kind of discussion is, I said that Intel was trying to fix those problems later in life. They came up with a mechanism which is called user processor interrupts. And those problems exist, but the idea is that if you have two processes running P1 and P2, and P1 can send an interrupt straight inside P2. And if P2 is not running, which is like P3 is running here, then there is a slow path, and kind of those problems exist because you cannot send it. And then you go through the kernel. But if both of them are running, or it's the same process and you want to kind of synchronize between the cores, then maybe it's like both of these are P1, and those are just threads of P1. Then it works. But again, I wasn't immediately sure what Intel was going after. They have a couple of slide decks, but no one really sees an appealing use case for why such simplification mechanism is needed. But they roll it out, so it exists in modern CPUs, but it's a little tricky. So again, so just make sure that, okay, maybe you know about it, but essentially you kind of can. I mean, and I had a student in my class last year. I asked them to, look, guys, can you build something similar and compare the overheads of this? Essentially, like build everything in software, like we just discussed, versus using this hardware mechanism and see like what is even the benefit. Fortunately, that person they didn't make enough progress, so I don't have a concrete answer. So I don't know the answer myself. It's an interesting topic of research. But like again, not clear, and we'll come back in like let's first discuss it. It was kind of far into the woods to begin with, but let's just discuss the simple case, build it as a homework, then everyone knows how it works. Then we come back and we'll discuss what possible corner cases and whether we can optimize this high frequency trading case and how. And maybe like we'll come back to it and try to solve it. Especially on a simple kernel like the one which we're building. On Linux, it's much harder because of like the number of corner cases is much larger that this thing has to work. On a simpler kernel, most likely it's doable. Okay, but I wanted to make sure that first, like that we understand how the interrupts works, because really we want to code them up, right? And what is it I wanted to like, okay, that's for the babies, we kind of understand it. Okay, so the figure number one, which we need to understand is that, which we already kind of talked about. So the hardware has a register, it's an interrupt descriptor table register, which has a virtual address which points to the beginning of the interrupt descriptor table. So the register is gray, which is CPU. The memory, the interrupt descriptor table is in memory. And you can have multiple. Each core can have its own table. We'll talk about it. You can reload the interrupt descriptor tables when you switch processes, or change entry in the interrupt descriptor table if you want to play tricks like this. Typically, it's not done, right? But okay, just let's remember the simpler case. And my slides are for 32-bit system, but roughly speaking, and we can switch for a second. At a high level, what matters here is the address of the handler itself. So on this slide, it's 32 bits. On 64-bit machines, everything is twice as large, and so we'll have a 64-bit address. And the segment selector is this CS register, which allows you to switch essentially from privilege level 3 to privilege level 0, because depending on how you configure it, it can lead you to a different privilege level, right? Quickly, what happens when you receive an interrupt, right? What happens is the following. So let me figure out this. Where is it? So if you were running at some, let's say, if you were running a user level, slides from x to the 6. So imagine your stack. So imagine your instruction pointer was somewhere here, like executing normally some user code here, right? At this point, let's consider the concrete example of vector 32, which is a timer interrupt. So the hardware says, okay, hardware receives some kind of a signal. So depending on where the timer sits, is it external to the CPU or internal? I think both setups are possible. And at this point, CPU kicks some logic and essentially, remember this, my wonderful slide. So typically CPU does fetch, decode, execute, loop, right? Here it says, okay, look, by the way, there is an interrupt pending. So instead of like fetching the next instruction pointed by the instruction pointer, I will go and try to process the interrupt. And the logic is like this. You say, look, the hardware has this interrupt descriptor register, which points to the interrupt descriptor table. So essentially, the operating system configures it. The hardware send a number. So in our example, it's number 32. We say, look, we will pick an entry number 32 from this table. As I said, two major parts of this handler, of this entry in the interrupt descriptor table, are pointer to the handler itself. So this is the function which will start executing vector 32. Again, if we not considering exotic cases, it's located in the kernel address space, not accessible by the user. And you say, look, if I were running at privilege level 3, I want to switch to privilege level 0. What will happen is that this code segment, which sits there in the interrupt descriptor table, so this one, segment selector, will loop back to the global descriptor table, pick a new entry, and this entry will have privilege level close to 0, right? If you leave this at 3, then you will continue running at 3, right? Make sense? Okay, cool. So there is this subtle detail, right, which we were discussing in the undergraduate x86 class. The hardware cannot trust this stack because if the user is malicious, it can put ESP pointing to some page which is not mapped, and then you will essentially, upon receiving an interrupt, you will trigger a page fault. So how do we protect against this? Do we remember from x86?
Do we create a new stack?
We create a new stack. So we create a special kernel stack, which we allocate in a kernel memory. So it's like, say, stack for level 0. And how do we switch to this stack? How does hardware find this stack?
TSS?
In the TSS, man, you graduated. I'm proud of you. So yeah, you're right. So to locate this process stack, hardware uses yet another data structure, which is called task state segment. And this task state segment is pointed by a special task state segment selector, which sits inside the global descriptor table, right? And at this point, TSS will have a pointer to a kernel stack, right? And this way, like if you were running at user level, interrupt hits you, you say, look, whatever, I'm switching back into the kernel, but I always have a fresh stack. So and that protects you from like certain like a range of attacks. So you can thought it through and everything kind of seems to work. Any questions about how it works?
So some of these like hardware specific structures like the IDT and the DSS, I'm guessing like you just mentioned Intel for DSS. So I'm guessing Intel or specific companies play roles in the manufacturer and normalized usage of these.
Yeah, no, it's only, this is Intel specific.
Okay, this is Intel.
Like ARM will have a slightly different layout of everything. Conceptually, it will be similar. So it's enough to understand it once, and you think, okay, is equivalent mechanism available in ARM? And ARM is actually way more elegant. Like I don't know why. Often they like maybe it was they had more time or something. Intel is always like a little awkward. But the moment you understand it once, you say, look, how do I switch to a kernel stack? And then you ask it the question. Typically, you can answer, right? So we are on Intel right now. Any other questions? Okay, so, and just to make sure that all of these, I have a diagram of this interrupt descriptor table. This is my table, which goes from entry 0 to entry 255. The first 32 entries are Intel specific, the other configurable by the operating system, right? But like it always follows the same protocol. So for example, if you suddenly like divide by 0 here, right, in user level, well, everything is the same. It's just that the number, interrupt or exception number, will be different, right? Make sense? Okay. So, and what's important here from the point of like, okay, you say, look, I wanna build a kernel which enables interrupts. So, okay, it doesn't seem like a super duper hard task. You say, look, I will define this 3 data structure, interrupt descriptor table, global descriptor table, because I need this connection to switch to a different privilege level, and you need the TSS to switch the stack. You define them because you say Intel open and Intel development manual, it gives you exact pictures of how it should, like exact layout, kind of like these pictures, but for 64-bit mode. You carefully define those in Rust. I'll show you how to do it. And then you say, look, it seems doable, like everything will be connected. I can start running, right? A couple of things which are also important here. So the hardware like follows a specific protocol, and it saves specific bits of information when it goes through this kind of transition, right? Do we remember what the hardware is saving? I kind of talked about this protocol, like the hardware says, okay, I will give the IDT free. I say like vector 32, I will find entry 32. I will read the handler stapler, efforts, I have to jump to the handler. I will like switch all of this TSS and GDP, switch the privilege level, and switch to a new stack. The question is, what is saved on this stack? So what does hardware save on this?
Oh, I was about to say, I think this is wrong, but I was about to say that it first has to save the registers that the process was using that just got suspended. But I don't think that goes in the stack. I think that goes into like a dedicated place in the process.
Those are possible hardware design choices, but that's not how it's done. Intel followed actually a meaningful design kind of design process or something. They said, okay, we're only gonna save the minimum amount of things which are changed during this hardware transition, meaning that it's impossible to know, like at the very first instruction in the handler, the register AX will not be changed. So it's there. So it's up to you to save it or not. But certain things are changed. And what are those things? That's how you should think about it. Just remember those 5 things which are changing.
Stack pointer, base pointer, instruction pointer, and the thing that is registered.
Almost there. It's like you're like 25% correct. You guess 2 out of 5. I don't know, maybe 20% correct.
I remember there is this called CS. I remember the E flags
Yeah.
and instruction.
Yeah. And what else? What is changing? Again, if someone really like pushes you into a corner and says, okay, I'll give you 5 minutes, but tell me what is changing. By looking at this diagram, you can recover this information. Like stack, right? Exactly. So the stack is also changing. So we have to save it. So stack pointer, like in 32-bit, it's ESP, and the stack segment, right? Because like roughly speaking, on Intel, those are like a fat pointer. It's not just a pointer, it's also this selector, which allows you to use an entry in the global descriptor. Okay, but this is kind of logical, right? So let me explain. Obviously, if you were running here in user level, right, the instruction pointer is changing because now the instruction pointer will be sitting here, right? Along with the instruction pointer, always the code segment changes because like there were like fat pointers, right? So on Intel, everything is a fat pointer, right? So that's why we're saving these two. The same argument for the stack, because if you change the stack, so you were running here, okay, whatever, maybe that was your stack pointer ESP, but sure, you're switching to a new stack, right? So this value of ESP is gone, right? So you have to save it. And of course, along with the ESP, you save stack pointer. And the only mysterious thing, which is hard to guess and probably cannot get from this figure, but why is the E flags changing? Do we remember? Again, it's a little bit of a Intel wisdom. E flags is the register which also holds, like E flags holds a bunch of flags. One of these flags is interrupt flag, whether the subsequent interrupts are enabled or not. And as part of this transition, remember I said that you can configure the entry interrupt in the interrupt descriptor table to say when you go through this entry, either disable subsequent interrupts or not. And so you don't know the value of this bit in the old E flags register, right? Because it's gone, because you say, look, I disabled it, but you don't know whether it was enabled before or not. You can ask yourself a question, damn it, like if it was disabled, how was it even triggered, right? So what's the answer here? Well, give me an example of an interrupt which is delivered when the interrupts are disabled. Again, you think logically, certain things are unavoidable. If you're dividing by 0, then there is no way forward. You cannot disable division by 0. You're already dividing. It's kind of like the bullet is there.
So I guess for those first 32 vectors.
Correct. So those are like synchronous conditions, right? Something is wrong. You're touching a memory which is not mapped. You're dividing by 0. So you go through the interrupt descriptor table, and here there might be a flag which says whether the interrupts are enabled or disabled, right? So that's why you save E flags, the old state of this E flags register.
And those were the CPU defined ones, we just talked, like divide by 0.
Yeah. We'll just talk in a second. Yeah. So those are synchronous, right? Or maybe you're just invoking an X40 instruction because you're trying to do a system call, right? Which is a more or less exotic example. But you just literally in x86 we say in X40, and you're just getting into the kernel as part of the system call. And you can control whether this flag disables subsequent interrupts when you do this system call transition, right? Bonus question, like, is it flag set or not? So like, do we disable interrupts when we do a syscall in x86?
So like, so this vector 40 would be disabled if E flags was set. Or rather, like if interrupts were disabled, the vector 40 in this example would also be.
No.
Oh, vector 40 was true.
No. Okay. So that's a good kind of, again, a good lead into another. There are two flags. It's the flags.
Okay, I guess then my
No. You're right.
first question would be: does the CLI and STI commands, instructions, do those modify the E flags, or do those modify?
Okay. Wait. Two things. Like two flags. One flag controls whether when you go through this interrupt handler, either like entry in the interrupt descriptor table, whether the E flags inside the E flags register will be set or not, right? So you say, look, if and I forgot like again, so clear is 0, right? So if you say interrupts were enabled, I go through this transition, I set this one to 0, so it means that further interrupts are disabled, right? That's what's controlled by this flag. The second interesting field is the descriptor privilege flag. It's 2 bits. And this one controls whether you can invoke X40 or not. Because letting user to invoke X, whatever, 13, which is page fault, if I remember correctly, will confuse the system. Because if user can do int 13, and the system faithfully goes through this transition and says, insist on the fact that if there is a page fault, your memory management subsystem is completely confused because really there is no page fault, but the user just plays an attack on us, right? So, and for most of the entries in the interrupt descriptor table, this DPL will be set to 0, right? Which means that user cannot invoke this instruction. It probably will go into another exception, which is called protection violation, or what is global protection for DPL, right? Because its user tries to do something wrong. And only for the vector x40, we will set this to privilege level 3, allowing the user to invoke this interrupt and go through this transition, right? But meanwhile, we still have control whether we want to set 0 or 1, or whether we want to disable subsequent interrupts on the system call, right? And it's a range of design choices, and you can make different decisions. But do we remember whether x86 leaves them on or not? It should leave them on. So why?
I did PintOS, and I think they also.
PintOS says off, subsequent off. Actually, I have no idea what PintOS is. I mean, I've heard of it, but I never knew. Yeah. So, what was your intuition? Why do you want to keep them on?
Like in case the system call as an exception.
Well, hold on. Exceptions are always on. You cannot
Okay,
disable it, right?
Then
Like now we use the terminology that exceptions are synchronous, interrupts are asynchronous.
Right.
So
Okay, so
this
then
flag
that would
only
also-
controls the interrupts, right? The synchronous events. So what's the benefit of allowing them? Versus the benefit of disabling them, like PintOS.
If you disable them, then you can do this is called more gracefully.
Correct. So in a way, if you say, look, I disable subsequent interrupts, you have a guarantee that for the duration of system call, nothing can preempt your system, and you will run to completion. And while your code might be simpler to code, right? Because you know that, you're looking at some data structure and some kind of a linked list, and you say it will not be changed because you don't have to acquire logs or something like that, unless you're running on a multi-processor system, right? That's fine, and maybe that's why PintOS does it. I don't know if they do that. We do it in our wonderful operating system, which is called Atmosphere. We disable them because we verify everything. Like we verify the behavior of a syscall handler, and we didn't get to the point where we can verify it if it gets preempted by another interrupt. Simply verification. Cannot build a mathematical proof. So we disable them in Atmosphere. In PintOS, maybe it's disabled because people are coding a very simple syscall, right? What's the disadvantage?
If it's handling an interrupt and another, another device tries to cause an interrupt.
Well, if it's a user which does in 40, x40, which is 64.
Well, interrupts are asynchronous, right?
Well, good question. So is this interrupt asynchronous?
I guess that one.
This one will be synchronous. It's very confusing. When I was your age, like I couldn't make a sense of it. I was thinking, okay, like how is it even work? So it's a real instruction. You can code your code, and you put in assembly, you can put int x40, and then it synchronously triggers the transition through the interrupt table. And if you say DPL is 3, this transition doesn't trigger a general protection fault because we allow it. The operating system kernel says, okay, user can invoke this int x40. If user tries to invoke int 13, which is a page fault, then we configure DPL to be 0, and then we say user is trying to fool us, so it's a general protection fault, will kill the process, right? Right? But what's the disadvantage of allowing interrupts while you transition through this synchronous, you invoke this instruction synchronously, it cannot be disabled. So you say, like, even if the interrupt flag is off, it still goes through, right? And you transition from privilege level 3 into privilege level 0, you run the syscall what's the advantage of leaving interrupts on?
I'm kind of thinking in terms of RTOS, but if you have certain deadlines.
Right? Wow, for sure. RTOS is a great example. It's a real-time system. You say, look, I have to steer the wheel, otherwise I'm off the, like I'm into the bushes or something, right? So when you configure the timer interrupt to like, to send you a notification, let's say 10 milliseconds or whatever, like on modern Intel hardware, in the past, you could just choose between a fixed set of times. On Intel today, you can just actually say number of cycles, and which is very fine grained. So you can say, look, I will run for really like 5,000 cycles, and then I want to steer the wheel. RTOS is a great example. It needs interactivity. And you say, no matter what user is doing, maybe you're playing music here or something, I want this interrupt. Like, and there are ways, and we will talk about it later, to make ways to confuse the system into running a very long system call. So for example, maybe you say, do an M map, like map a very huge region of memory. It will take forever. Maybe it will take for like half a minute to map. Okay, half a minute is like a stretch, but half a second. But at this point, your RTOS goes into the woods, right? And it kills there. So this is tricky, right? That's why x86 leaves them on. It says, okay, look, we're kind of above, it can just maybe not, but they say, look, we will leave it on to illustrate this case that system calls can be preempted with interrupts. And that's kind of a practical, when you call something real, RTOS-like style, or you, like again, still care about interactivity in your high-frequency trading systems, you will leave them on, right?
If they're naive, like if we have it at night, wouldn't that mean that other interrupts could be lost? Like if an external device sent one, it would be
Right.
lost. So I'm pretty sure the solution is that you have like a data structure that stores any received ones.
Yeah,
and
yeah,
you
yeah.
just do-
So CPU will stash them and kind of will remember, and you can stash multiple. And there is, I believe, again, I never looked at it in details. There is some priority, and some of them will be higher priority than others. And it will, the moment you re-enable, then it will get delivered. However, like the question is like how you define lost. Because the fact that you set a flag here saying, I have an interrupt, it probably means that you received enough packets, like 32, for example, and you want to process them because RTOS says, okay, I want to receive packets as fast as I can. But at some point you say, this device itself might have a limited capacity. Maybe it's like a 1 GB of onboard RAM where it can save packets, right? And after that, it says, okay, emergency, like I want to send an interrupt, really, because we're approaching, like maybe it was 0.7 GBs, right? But then nothing is happening. The system call is running. New packets are arriving. There is no place to store them. At this point, you lose packets. Losing packets is not a big deal, but if we are like in the RTOS domain, maybe this is a signal like steer the wheel or something along. The sensors are saying, okay, you have to really steer the wheel. And so you can still lose. So the fact that the CPU stashes or like remembers the fact that interrupt is waiting doesn't mean that you really not losing a physical event in a physical world, because there might be no space to save it. So you have to be careful about
Are
it.
there implementations where instead of specific interrupts deciding whether or not to turn it off, it's the other way around, where if you receive an interrupt and it's an emergency type of interrupt, then it preempt another interrupt. So instead of deciding like, oh, this nmap that takes a second, you can't be preempted at this time. It would be that other interrupts did decide whether or not.
That's correct. And Intel has this magical interrupt, which is called non-masking. Vector number 2. Vector number 2 says, okay, you cannot disable. Yeah. And then it's your game. It's a little tricky because it's like an emergency resource. Maybe, you sense that the power is off and you really need to shut down cleanly. Maybe it's some kind of emergency event. I only used it for debugging information collection, meaning that we do this, we use VTune or perf, which profile, like essentially, which you can configure the hardware to say, preempt me every time 1,000 cycles lapses, or maybe you receive, you go through 1,000 branches in hardware, right? And so just to make sure that collection is precise, we process it through the non-maskable interrupt because we don't care what the system is doing because we're collecting even if its interrupts are off or on, but we want to receive an interrupt, right? So there is this idea, and there is this one special interrupt, non-maskable interrupt, which cannot be masked, which does not obey this interrupt flag. It will always be delivered, and it's asynchronous. And you have flexibility. You can configure which hardware events will be routed through this non-maskable interrupts. I can't be wrong because I never did it in practice myself, but I'm pretty much sure that you can even configure network packets to be delivered as through non-maskable interrupts. And it's like, this is one example, good example of share, because you say there is only one non-maskable. What if I have debugger events, my profiling events, my network packets, so you share it, and then you have to, your device driver or the handler which processes the interrupt has to be smart enough to distinguish. So you have to read something from the hardware like this bit and say, are you sending an interrupt? The hardware says, no, it's not me. Then you say, look, and it's probably profiler or something like those. So it can be shared, and I'm pretty sure it can be configured, but I don't think, unless you have a very strong use case, like again, maybe RTOS, it's more of an emergency thing. So probably you have to think about your system that like normal interrupts are enabled, disabled, and non-maskable interrupt is some emergency mechanism. Another, we also send inter-processor interrupts. So there is a mechanism to say one CPU can send an event to another CPU, inter-processor interrupt, to notify the CPU about a specific event, whatever, like semantically it can be different things. Typically, it's like just start doing something. And this inter-processor interrupt will also be routed through non-maskable interrupt because we wanted it to be fast, but it's not necessary, not always true. Yeah.
So this IPI thing, is it like processor one?
Yeah.
Invokes the interrupt?
Yeah. And it's kind of logical because you say, look, again, like it's part of the scheduling where you say, look, I have a higher priority things which I want to process. This runs some low priority thing. But I really from the network card, I detected that we have to start running and we send an IPI and then like essentially can preempt whatever was running there, right? Makes sense? Okay, so, this is the table. So since we're on this slide, let's quickly take a look. Again, it's not updated and I should probably update it. So I will update it by next time. So on this, only 19 were defined by Intel. I'm pretty sure that now they defined more here. So, but still they only reserve the first 32. So everything from 32 and up, they call them maskable interrupts because these are configurable by user as asynchronous events. So they obey the interrupt flag, right? So interesting examples here. And again, like we'll get back to it next time as well. Division by zero, well, not so much interesting, right? There are two debug interrupts, and one is a software breakpoint, if I remember correctly. So I think it's this one, right? So you can actually say, look, like you invoke a specific instruction which is int3, and that's essentially that's how you implement software breakpoints. And the hardware debug interrupts, this is like hardware breakpoints, right? Non-maskable interrupt, we kind of talked about it. So overflow is specifically to react to this into instruction, which I don't know if anyone uses anymore, but there.
So this breakpoint, again, like when we look at the interrupt descriptor, every exception already has a associated. But if I'm debugging multiple programs using different debuggers, shouldn't they all be pointing to different code segments?
Correct. So the way it's implemented in practice is that
is there also like a shared vector?
Yeah. So this multiplexing is implemented by the operating system kernel. So essentially, I mean, it might look a little unusual when you look at it for the first time, but essentially you say, look, I have a process P1. I have another process which implements the debugger, GDB. And there is some kind of a plumbing that they are connected, right? And at some point, GDB says, look, I did this in 3. There was some instruction here, maybe it was addition, and I want to implement a software breakpoint. So GDB says, okay, save this old instruction, put this in 3. It's 1 byte instruction. So when you hit it, you cannot like, it's on purpose 1 byte, because you cannot like pass control to the second byte. And at this point, this goes into the kernel. Plumbing here is that, okay, there is some functionality with debugger. You look at the process, you look where the GDB is, and you pass control to GDB. So kind of this multiplex and stuff like that. But okay, what I wanted to like important cases here are debugging. Yeah, we'll come back to it. But like our wonderful suspects, okay, I was strong. Page fault is actually 14. So we need to remember general protection. You will see it a lot because if something is misconfigured, there will be like, there might be a general protection fault. Another useful one is a double fault, meaning that this one happens when the first interrupt is already ongoing. So essentially, you maybe started processing a page fault and the hardware said, okay, I will, and you touch a page and another page fault happens. And this, at this point, not the page fault is delivered, but the double fault is delivered, right? Like if you screw up your TSS, there is specific condition when you will get this invalid TSS. What else is like things like invalid opcode, like this is undefined behavior. You see it when you disassemble Rust or something. They insert this invalid opcode to make sure that you will get an exception when this specific thing is reached. Like unavailable mathematical coprocessor. It's like the era where the floating points were implemented like kind of on a GPU-like device. Probably will never happen to you, but essentially you will have to look into the table, but like double fault, general protection fault, page fault will be your essentially most common, right? So just make sure that you understand them. We'll take a look a little bit more, but as you essentially the workflow, we develop this infrastructure, we install the interrupt descriptor table. At least when we get a fault, we'll bring something on the serial and say, look, this is the fault, this is the reason, and this is your starting point. And also the QMU will tell you that, okay, a specific fault happened. So you can take a look and start debugging from there, right? Makes sense? But what I wanted to get to, we looked into this, right? And we say, look, this is happening when there is a privilege change, right? There is this awkward nuance that if you're already running, so for example, our case where we enter with a syscall into the kernel, not disabling the interrupt. So we're already running inside privilege level 0. And at this point, timer interrupt shows up, right? At this point, the hardware follows a similar protocol, but not identical, right? So it's kind of like, it's a little simpler, right? Because the hardware says, look, guys, I simply just, I figure out the pointer to the interrupt descriptor table. I will figure out the vector. I will do this code segment, go into the GDT. But it like we were already in like this one points to privilege level 0. So sure, there is no privilege level switch. And at this point, the hardware will not switch the stack by default, which means that it says, okay, the stack is, wow, we trust the stack because we're already running in kernel set. There is no reason to change, right? And so since the stack does not change, you don't have to save those stack pointer and stack segment, right? And instead, you just, instead of 5 things, you save these 3 things. If flags is changing because we disabled interrupts, whole segment is changing because, and this whole segment instruction pointer because it's a path point, right? Because it's John handler. So you only save 3 things instead of stack 5, right? Just because the stack is not changing, right? And like I forgot to mention that this error code like a subset of these events in this, which are defined by Intel in this table. And I'll go, I don't remember by heart which ones are which, but the point here is that some of them actually push an error code, like exception specific error code on the stack, right? So like some of them, not all. So some of them do, some of them don't, which creates like, this is where I'm trying to get to this. It creates this irregularity of the stack. So essentially you say normally, I mean, if there is a privilege change, I will take 5 things, but occasionally there will be a 6th one, it's an error, but not always. And if I don't switch the privilege level, then on the stack, there will be just 3 things and maybe occasionally an error. Okay, that kind of sucks because you say, look, I really wanted to code my function in a language like Rust or C or something, right? But we don't even know even like what will be the stack layout when it will be invoked, because like depending on how it was invoked, maybe on the stack there are like 5 things, maybe 3, maybe 6, maybe 4, right? And at this point, we have to decide what to do. Okay, so we have like 5 minutes. So like just quickly, let's brainstorm for a second. I want to write a function foo, which is a handler, like in Rust or in C, right? It will start executing on this funky stack. Let's imagine the privilege change happens. So you save those 5 things here, and maybe there is no error code, so your stack pointer is here when you start executing this function, right? Most likely, you want to somehow pass a pointer to this stack so you can like whatever, some kind of a stack frame or interrupt frame, which like matches the layout of this stack, right? Interrupt frame. And so you can like do IF EAP, and at least you know where you were running, where the page fault happened, right? Make sense? So you kind of try, at this point, the question is, we wanna connect high-level language like Rust or C with low-level hardware interface. How are we gonna do it? That's the question which I'm trying to ask you. Like, let's think about it for two minutes, and then I will answer on Monday. How do we want to connect? Like, ideally, like, I do not advocate to write assembly. Like, only some minimal sequences of assembly are necessary, but everything else ideally should be high-level language like C or Rust, right? The question is like how to make this plumbing. Do we remember how it was done in x86? No one. Okay, so let's stop here. So we will have a couple of minutes, but it's a good like go home and think about how to connect. I mean, I explained the hardware interface to some level of details, right? As you code against it, it will become concrete. But now the question is how to make this connection using available tools. Assembly, Rust, whatever. If you think in terms of C, think in terms of C.
That's the kernel stack.
Yeah, let's imagine it's a stack on which this handler is involved.
So
If you're so exotic that you want to process it in user level, you'll have the same problem. But
so the problem you're stating is that like, it's variable now.
Variable, like solve the simple problem first. Imagine you have a fixed layout, start with this, and then switch generalize to different cases. Okay, so let me stop here. So I'll see you on Monday then. Homework or tomorrow during the office hours at 4. What else? I will try to prepare the next homework over the weekend so I can assign it hopefully on Monday, or maybe even sooner, but it will be about interrupts. But again, like complexity will be about the same. Maybe debugging will be a little harder because like hardware will start glitching, but I will give you pieces of code. Maybe not explicitly like this time, but like kind of you will be able to find them. Okay, so thank you. See you then